Hello there and welcome to this channel. Today we're going to talk about the uniform probability of a finite set. Let omega be a finite set, with omega being the void set, A the parts of omega, cardinal of A, the cardinal of A, with A a subset of omega. The probability of A is equal to the cardinal of A on the cardinal of omega. The probability of our singleton little omega equals 1 over the cardinal of our universe, which is also equal to the cardinal of our singleton over the cardinal of omega. The first point states that the number of permutations or bijections of a set with n elements, for instance 1n, is n factorial, because if you choose one place you have n choices left, then to choose for the second place you have n minus 1 choices, leading to n times n minus 1 times and so on up to 1 choices of position for any number element. Secondly, the number of arrangements of k elements in a set of n elements with k smaller or equal to n, or injections from 1k to 1n, is akn equals n factorial over n minus k factorial, because you only consider the first k choices over n times n minus 1 times and so on up to 1, and that's exactly the following equality, where we end up with k choices. Let's say now in the third point that we have 7 positions and we want the possible number of sets with 3 pieces, 3 gold coins. So we have 7 positions, P1, P2, P3, P4, and we have 7 gold coins, but we are only interested by 3 gold coins. So 7 factorial over 7 minus 3 factorial represents, as we saw, the number of arrangements of 3 pieces, 3 gold coins in a set of 7 positions. But the group in the first configurations is the same as the groups in the second, third, and fourth configurations. So we need to divide 7 factorial by 7 minus 4 factorial over 7 minus 4 factorial by the number of permutations for a set of 3 elements, because in 1, 2, 3, and 4 we have the same elements. We can get rid of the 3 factorial permutation to create groups. For each configuration we make a choice to place the 3 pieces in a specific order, but it's irrelevant because, as we saw, we end up with a group composed by the same pieces in each case. So dividing by 3 factorial allows us to regroup 1, 2, 3, and 4 and the others into this, with the 3 pieces we see being the pieces 1, 2, and 3 in any order. So, to sum up, the number of subsets with k elements in a set containing n elements is n choose k equals n factorial over k factorial times n minus k factorial. Another way to understand this formula is to say that the number of arrangements of k elements in a set containing n elements, so n factorial over n minus k factorial, is also equal to the number of subsets with k elements in a set containing n elements times the number of permutations for subset with k elements. So n choose k times k factorial equals n factorial over n minus k factorial implies that n choose k equals n factorial over k factorial times n minus k factorial. Example: birthday dates. We consider a class of n students. We are looking for the probability that at least 2 students were born on the same day. We assume there are no leap years. Omega, our universe, is equal to 1/365 to the power of n, with n equals, with w equals w1 up to wn, or omega equals omega 1 up to omega n. Omega I is the birthday of student I. The associated natural sigma algebra is the parts of omega. We choose the uniform probability on omega. Let omega be the event at least two students were born on the same day. The probability of the event A is equal to 1 minus the probability of the opposite event, which is equal to 1 minus the probability of all students have different birthday dates, which is equal to 1 minus the probability of the set where omega is such that omega I is different from omega j, with for all I different of j, which is equal to 1 minus the cardinal of this set over 365 to the power of n, equals 1 minus the cardinal of the number of injections from 1n to 365 over 365 to the power of n. So, to sum up, the probability of A is equal to 1 minus 365 factorial over 365 minus n factorial times 365 to the power of n equals Pn. We obtain the following numerical values. P20 is approximately equal to 0.411, P23 equals approximately 0.507, P50 is around 0.970, and P366 equals 1. To get those values, we need a good calculator or some deeper reasoning. Indeed, 1 minus Pn is also 365 minus 1 over 365 times and so on up to 365 minus n plus 1 over 365, which is also the product from k equal 1 to n minus 1 of 1 minus k divided by 365, which is also the exponential of the sum of ln of 1 minus k over 365. If n is not tall, an approximation of this sum is done replacing ln of 1 minus x by minus x and using the following formula. The sum of k equals n times n minus 1 over 2, which leads to 1 minus p1 being approximately exponential of minus k divided by 365 equals exponential of minus n times n minus 1 over 7 and 30. Approximately equals to which is approximately equal to the exponential of minus n squared divided by 730 by comparative growth. If Pn is around 1/2, then 1/2 approximately is equal to exponential of minus n squared divided by 730, which implies that minus ln2 is approximately equal to minus n squared over 730, and so we end up with the square root of 730 times ln of 2 equals n, which is around 23. To be more rigorous, we can use the bounding valid for all x strictly greater than 0 and strictly smaller than 1. We have the red framed inequality, the red frame bounding. To obtain these upper bounds, we start from the power series expansion. ln of 1 minus x equals minus the sum of x to the power of k over k equals minus x squared over 2 minus x3 over 3 and we have our right hand bound, which immediately shows the right hand bound, while the left hand bound is obtained by the enumeration of ln of 1 minus x by minus x minus 1 half times the sum of xk from k equals 2 to infinity, which is equal to minus x squared over 2 times 1 minus x. We also need the sum of first squares, or the first squares, which is established by induction. If x is smaller or equal to n minus 1 over 365, then minus 1 over 1 minus x is greater or equal to minus 365 over 365 minus n plus 1, hence the rigorous bounding. Minus 365 over 365 minus n plus 1 times x squared over 2 is smaller or equal to minus x squared over 2 times 1 minus x, which is strictly inferior to ln of 1 minus x plus x, strictly smaller than minus x squared over 2. We take now x equals k over 365, then we obtain minus 365 over 365 minus n plus 1 times k squared over 2 times 365 squared is strictly smaller than ln of 1 minus k over 365 plus k over 365, which is strictly smaller than minus k squared over 2 times 365 squared. We pass to the sum, and we obtain the red frame bounding, because ln of 1 minus pn is also equal to ln of exponential of the following sum, which is equal to the sum of from k equal 1 to n minus 1 of ln 1 minus k over 365. Now we turn our attention to the related problem. We seek the probability of the event B, that is, at least one student was born the same day as their teacher. By denoting x as the teacher's birthday, the probability of the event B is equal to 1 minus the probability of the contrary event, which is all the students were born on a different day from x. So, the probability of the event B is then 1 minus the probability of the set of the omega, such that omega I is different from x for all I, which is equal to 1 minus cardinal of such set divided by 365 to the power of n. We end up with the probability of B being 1 minus 364 over 365 to the power of n equals Qn, according to the 3 points we saw not so long ago, which yields the next numerical values. Q20 equals 0.053, Q23 equals 0.061, and Q30 approximately equals 0.079, and Q50 approximately equals 0.128, and finally Q366 approximately equals 0.634, as ln of 1 minus qn equals n ln of 364 over 365 equals n ln of 1 minus 1 over 365, approximately equal to minus n over 365, so Qn is approximately equal to 1 minus exponential of minus n over 365. We notice that the values of Pn and Qn are very different, although the statements of the two problems are very close. This is because in the first case, we have several pairs of student birth dates that can match, while in the second case, the teacher's date is fixed and we are looking for at least one student with the same date. Therefore, the probability is necessarily lower. Conclusion: as soon as a class or an assembly contains more than 23 people, we have shown that there is more than 50% chance that two people share the same birthday date, and we have also shown that it takes around 366 days for having a chance of 63% approximately to have someone with the same birth date as their teacher. So that's quite a lot of days. Thanks for watching. Don't forget to leave a like, a comment. It would help greatly for my channel to grow. And I'll see you in another topic related to math and science. See you later.